Welcome to the ICCII Design Planning Incremental Training. In this training video, I will walk you through the new features added in 2016.12. The information in this training video is confidential. Please do not disclose to non-authorized individuals. This is the second session of training, clock trunk planning. This is the agenda. We will introduce the terminology for clock trunk planning, and then we will have overview of the flow, tell you how to perform clock trunk planning, and then how to use GUI to analyze your result. This is the table for terminology we will use for clock trunk planning. First, what is clock trunk? It refers to a coarse-grained physical distribution of clock. It starts at clock source and ends at clock trunk endpoint. Clock trunk endpoint is an endpoint of a clock trunk. Clock trunk endpoint can be tool-derived, such as anchor buffers, block clock pins, or pins with hyphen out. It can also manually specified by users. Clock trunk arc. It refers to a file line used to show the connections in the clock trunk GUI. Clock trunk logic. It refers to pre-existing cells in the clock trunk. This includes every cell which is not a buffer or inverter. These two timing numbers with OCV are the terminology usually used in clock trunk planning reports. Worst negative slack with OCV shows violating inter-block timing path with OCV. Critical slack OCV may show inter-block timing path with positive slack. To see the OCV effect, user need to set timing delay in the timing constraints. The main benefits for clock trunk planning is to have better timing budget for the data path between blocks. It increases the common clock path, which adds more CRP delay. ICCII also provides interactive GUI, so user can see how clock trunk result in layout window, and then manually insert clock buffers. The clock trunk topology is repeatable, so it can be reused at top level. Clock trunk planning is implemented after pins are placed. It is done by two major steps. The first step is during block level, and second step is in top level. During block level, it inserts anchors for each of the clocks and estimates clock latency from the anchors to the sinks. During top level, it performs clock trunk planning. It inserts clock trunk buffers to identify clock divergence points. It estimates clock latency and the CRP for data path budgeting. Clock trunk planning supports many kinds of design styles. It is MIB aware, multi-corner aware, multi-voltage aware. It can operate on the current mode. It supports mixture of block capture at different stages. For example, planning stage, pre-CTS stage, post-CTS stage. It also supports different design planning flow, hierarchical abstraction view, and full netlist design views. The netlist can be MIB or black box. Currently only support channel style floor plan. A body floor plan is not supported. The required input and output. The first required input is the top-level hierarchical database. The database has to be pin assignment of the block is completed, and also timing constraints are loaded in the top and the blocks. The next is set timing delay - clock option. Timing delays for the clock path is required. Also, CTS constraint file. It ensures optimal accuracy for block level clock latency estimation. Also, it must be specified for each block in the CTS constraint section of the constraint mapping file. See the set constraint mapping file main page for detail. The output. User can use write clock trunk to write a tickle file in ASCII format. This can be used to recreate the top-level clock trunk in a new section. Clock trunk cells. This is topology-defined cells at clock diverging points. Estimated clock latency and CRP. Estimate values are used for database delay budgeting. This is optional inputs and outputs. The optional inputs, user can set clock trunk endpoints to specify clock trunk endpoints. If you have used set clock trunk endpoint, then you can use report clock trunk endpoints with option .script. It will output tickle file in ASCII format that contain the commands to specify the clock trunk endpoint in a new section. This page shows the command used in the clock trunk planning flows. The first step, you enable block level clock trunk planning during estimate timing. You can enable it by set app option -name plan.clock_trunk.estimate block latency with -value true. Then you specify CTS constraint via mapping file using set constraint mapping file command. Specify default driving cell is an optional step, but we recommend you to do so. Set app option -name plan.clock_trunk.default driving cell with -value with the library cell name. And then you do estimate timing. This is the same as the regular design planning flow. After estimate timing, you can specify delay factor for OCV estimation by using set timing delay -clock option. And then you perform automatic clock trunk planning by running synthesize clock trunk commands. The menu clock trunk planning is an optional step. You can use GUI tool and to see the file line of the clock trunk planning. And then you can adjust adding buffer by using the GUI. Once you have done clock trunk planning, you can write tickle script to replay clock trunk result using write clock trunks. After all the clock trunk is finalized, user can push down feed-through net pins by running push-down clock trunks. Why do we want to define CTS constraints? Because the clock trunk planning leverages clock tree synthesis engine. So we strongly advise to specify all known CTS constraints such as max transition and max capacitance. Also min-max routing layer, non-default routing rules, clock tree reference library, the driving cell constraints on block clock pins. Specify CTS constraints to ensure that the clock trunk planning produces realistic results and correlate with actual implementation. For example, if a driving cell isn't specified, the tool will assume infinity input transition, which greatly affects clock trunk planning results. Why do we want to specify driving cell? This is because the QoR of clock trunk synthesized with driving cell is better than the QoR of clock trunk synthesized without driving cell. The ways to specify driving cell constraints on block clock pins are listed below. The first one has higher priority. First, using SDC constraint set driving cell specified in CTS constraint file provided with set constraint mapping files. It allows each block, each clock, each corner, each pin has different specified driving cells. The second way is using new app option plan.clock_trunk.default driving cells. It allows per mode or global specification. Following example shows functional mode using the library cell buff8x1 and the other mode using library cell buff4x1. If user did not specify any driving cell, then clock trunk planning will automatically select middle size of buffer for driving cell. This slide shows how tool insert clock anchor cell and estimate clock latency in blocks. It specifies block level CTS constraint with the mapping file, set constraint mapping file. Then the estimate timing command performs the following operations. Insert anchor cell in the block if required, and then create clock trunk endpoint in the block by annotating phase delay from the anchors to the sinks. And then it performs virtual in-place optimizations. These are the commands we use for this step. After block level is finished, and then we perform automatic clock trunk planning at top level. We specify top level CTS constraint via the mapping file and define the rate factor as appropriate. And then we use the synthesize clock trunk command to automatically perform clock trunk planning at the top level. This command synthesizes a clock trunk topology connecting together clock trunk endpoints. It considers clock trunk endpoint phase delays. It also inserts guide buffer to maximize the common clock path between blocks communicating with each other. After we finish clock trunk planning, and then we can use the GUI to check our results. We use the clock trunk planning GUI to visually inspect and interactively modify clock trunk before or after automatic planning. CTS constraint and clock delay factor must be set before running the GUI. The picture below shows the clock trunk planning GUI is invoked from the Connectivity Analysis tool pull-down menu. And then you load data by clicking Reload. The tool opens a dialog box. Choose Automatic or Manual Clock Specification mode. Tool displays clock trunk for the selected clock. Trunk object details are available. By hovering the mouse over the object and viewing the info tip. By clicking on the object and viewing the query windows. This page shows how we use inter-block timing file lines. Timing file line connects to trunk endpoints. Its detail available in info tips and query windows. OCB means estimate CRP is considered. Now we also have color scale binning mode available. There are also other modes available, for example, Slack with OCV, number of violating paths TNS color scale, and number of paths between blocks. Clock trunk planning uses data path delay and the Slack from estimate timing to show inter-block timing file lines. The clock trunk planning performs clock latency and OCV estimation based on physical layout, CTS constraint, and derating factors. The latency and OCV estimation do not appear in timing report, so timer configuration is unchanged. Clock remains ideal. Latency and OCV estimate value are shown in the clock trunk plan GUI. They are available for data path constraint budgeting. Timing analysis information from the clock trunk planning GUI can be reported by the new command, report clock trunk QOR. We will see it later slide for more detail. Typically, clock trunk endpoints are automatically inserted in the block during estimate timing. Clock trunk endpoint can also be created manually using set clock trunk endpoints command. Clock trunk endpoint can be reported in a top-down fashion using report clock trunk endpoints -hierarchical option. Clock trunk endpoint declaration can be exported as a Tcode script using report clock trunk endpoint script option. Clock trunk endpoint can be removed using remove clock trunk endpoints command. User can also use GUI to improve inter-block CRP. We identify path candidates showing critical slack with OCV. Then common path can be improved by inserting a clock trunk buffer driving block pins First, we select two different blocks and click Add button. The second step, we review the object we just selected, and then we click Add Buffer button. And then you will see buffer is inserted. OCB estimation is updated. The timing result is improved. This is report clock trunk QOR command. Timing analysis information with estimate latency OCB done by CTP GUI is now available from the command line. Report clock trunk QOR prints a summary of inter-block analysis for QOR evaluation of clock trunk planning. You can also use an option dash from block to block. Report is sorted by inter-block WNS by default. Thank you for watching the training for clock trunk planning. We hope to see you apply this clock trunk planning flow to optimize your timing budgeting result.